Alright guys, let's get started. Today we're gonna continue on chapter number 4, and it has been a while since our last meeting. So at the beginning of the class, I want to use about 10 minutes to do the recap of what we have learned in chapter number 4. Yeah. So in chapter number 4, the topic is AC steady state analysis. And at the beginning of this chapter, we introduced a new concept called phasor. A phasor actually is a complex number. It can be represented by a letter z, which contains a times e to the power of j theta. A is the magnitude of the phasor, and theta is the phase angle. And a phasor is related to a cosine function. In other words, a cosine function can be represented in the phasor form, and phasor can also be converted back to the cosine function. Let's say we have a general cosine function representation, which is a cosine omega t plus theta. Omega is the source frequency. Okay. A cosine function can be converted or can be represented by a phasor form, which is picking the magnitude and phasor angle information. So the phasor of this cosine function can be written as a ej theta, and this is the exponential form. As we mentioned at the beginning of this chapter, a complex number can be represented by 3 different forms, right? Exponential form is one of these 3 representations. But in general, we always use the polar form, which is a simpler representation. You just need to write the magnitude and the phase angle information, a and theta. How about a sine function? A sine function can also be represented by a phasor, or can also be converted to a phasor form. A sine function, but we need to convert a sine function to the cosine function first by adding negative 90 degrees. Right? And then again we have the cosine function, and the cosine function can be represented to a phasor by following the above transformation, right? So this can also be represented as a e j theta minus 90 degrees, which is in the polar form, that is a theta minus 90 degrees, right? And sometimes we have minus sign here, then you just need to add plus minus here and plus minus here too. The same way, if you have a sine omega t plus minus theta, then here we have plus minus theta and plus minus sign here, the same way here, right? Alright, so that's the cosine function to the phasor, and this is a bidirectional transformation, as we mentioned earlier in this chapter. Alright, and we also introduced the concept of impedance. We already derived how to calculate impedance, how to find impedance of 3 commonly used components, right? They are resistors. For resistors, the impedance can be represented as ZR equals to R, right? We use sample Z to represent the impedance, and we use the unit of the impedance is omega. For resistors, the impedance is the resistance itself. For capacitors, the impedance ZC is 1 over j omega c, right? And omega is the source frequency, as we mentioned earlier. And the last one, inductors. The impedance is j omega L, and L is the inductance. Although resistance, capacitance, and inductance, they have different units, right? The resistors, for resistance, the unit is omega. For capacitance, the unit is farad, and for inductance, the unit is Henry. However, after you find impedance of all components, which in other words, you represent resistor, capacitor, and inductor with impedance, the unit becomes that should be ZC. The unit becomes a single one, that is omega. Right? So by using impedance, by converting source, cosine function represented source, to phasor and represent all components in impedance, we can convert an AC circuit to a DC one. And also, I remember in earlier of this chapter, I gave a simple example to explain how to do that DC to AC transformation, right? So let's redo that example quickly. So for instance, we have an AC source, which is represented by VT, and we have three components connected in parallel, and they are resistor, inductor, and a capacitor. Vt is represented by a cosine function expression, which is 50 times cosine omega t plus 30 degrees. Unit is volt. Resistance R is 25 ohms. Inductance L is 20 millihenry, and capacitance C is 50 microfarad. Okay, and we want to find what's the current IT flowing through the circuit. So to solve this problem, and also we also know the source frequency omega, which equals to 2 pi f, which equals to 2 pi times 60 hertz, and that can be calculated. That equals to 377 radian per second. Okay. Right, so with this information, how can we find IT? To do that, we just need to convert this Vt into phasor form, and then we find impedance of each component, resistor, inductor, and capacitor. Let's find impedance first. As defined, ZR, the impedance of a resistor, is resistance itself. So we just need to write 25 ohms here. The inductor, the impedance of inductor is J times omega times L, which is J times 377 times 20 times 10 to the power minus 3. Because here we have microhenry, we need to convert to the base unit, so we need to times 10 to the power minus 3, and that equals to 7.54 J ohms. And for the last one, ZC is 1 over J omega C, and that equals to 1 over J times 377 times the capacitance is 50 times 10 to the power of minus 6. Because the unit of capacitance is microfarad, you need to change that to farad by multiplying 10 to the power of minus 6. And that equals to minus J times 53.05 ohms. And some people ask why we have a minus sign here, because 1 over J equals to minus J. Okay. Right, so after we have impedance of all components, we can combine impedance just like resistors. All components, as you can see, they are connected in a series connection, right? So the total impedance can be calculated by sum all impedance together, and that equals to 25 minus 45.51 J, and unit is ohms. And after we have total impedance, we can calculate the current in the phasor flow by using voltage in the phasor flow divided by the total impedance, just like the Ohm's law, right? And the voltage, the phasor flow of the voltage source can be derived from the cosine function expression. And by using the cosine function to phasor transformation, we know the phasor flow of this voltage source is 1530 degrees, right? We just need to pick the magnitude and the phase angle information to from the phasor representation. And Z total is 25 minus 45.51 J. Alright, so here we need to do the division, but for complex number division, we need to convert both sides to the same to the same representation. In other words, you can either convert the top part from the polar front to the rectangular front, just like the bottom side, or you can convert the bottom side to the polar front to be aligned with the top side. I do the second way. I convert the bottom front to the polar front, and that would be 51.92, and phase angle is 61.22 degrees. That would be 0.96, and phase angle is 91.22 degrees. In case you forget how to do the complex number division, if you have two complex numbers and they are both in the polar front, we have A theta divided by B phi, then the result gonna be the ratio of magnitudes and the subtraction of phase angles, right? So that's how we do the division. And in case you forget how to convert a rectangular front to the polar front, the transformation can be represented as this. So the regular front, A plus BJ, equals to the square root of A squared plus B squared, and phase angle can be calculated as inverse tangent B over A. Okay. All right, so that's how we handle complex number division and how we convert rectangular front to the polar front. All right, so after we have this current value, but this is not the unit is amp, but this is not a time domain function, right? Because we want to find the result of IT, which is a time domain function. So IT can be obtained by using the inverse transformation from the polar front to the rectangle, from the phasor to the cosine domain function, to the time domain function, by using the magnitude information 0.96 cosine And here omega should be the same omega with the Vt, because the circuit is powered by this power supply, is powered by this battery, and the source frequency is 377 radian per second. So we just need to write 377 here times t plus the phase angle, which is 91.22 degrees. Unit is amp, right? So you see, by using the phasor transformation and impedance, we can easily slope an AC circuit without applying any differential equations, without setting up any differential equations and slope those differential equations. So that's the recap we learned in the previous class. And in today's class, we're going to continue on this chapter and give you guys more examples of using impedance and phasors to slope AC circuits. Let's start with a new circuit. So in this question, we want to find what's the voltage and currents. Find the voltage and currents in the below circuit. So in this circuit, we have a voltage supply, and we have resistor, an inductor, another resistor, and a capacitor. Okay. Vs is given in the phasor form, which is 2460 degrees. Unit is volt. The impedance of the first resistor R1 is 4 ohms. For the second resistor R2, the impedance is 8 ohms. For this inductor, the impedance is 6J ohms. For this capacitor, the impedance is minus 4J ohms. Okay. And the voltage we want to find is the voltage across the inductor, which is named as V1, and the voltage across the capacitor, which is named as V2. Let's name it VL and VC. Okay. And for currents, we want to find is I1, which is the current flowing through R1, and I2, which is the current flowing through R2. So our goal is to find those variables, I1, I2, VL, and VC. Right, so how to solve this problem? If you compare this problem to the previous one, a very obvious difference is in this question, in the previous question, the source, the voltage source is represented by a cosine function, which is a time domain function. But in this example, the source is directly given by using a phasor. So in other words, you don't need to do the cosine function to phasor transformation, like what we did in this part, right? And another benefit, another convenient point in example 2 is that all components are given in impedance, so you don't need to do you don't need to find impedance of all components like what we did in these 3 steps in the first example. Right. All right. So with since the question has given us all those necessary information, we can solve this problem directly and just treat it as a normal DC circuit. Okay, we can treat all components as resistors, but the special point is those resistors have complex number of resistors. That's the only difference between DC circuit analysis. All right, so there are several ways to solve this problem. The simplest way maybe we can use nodal analysis. Okay. Method 1, nodal analysis. So as we mentioned in chapter number 2, in nodal analysis, the first thing you need to do is to identify nodes in these circuits, right? In this circuit, we have a power supply Vs, resistor, inductor, another resistor, capacitor. We can define the bottom one as a node, right? That's the conjunction of these three branches, and the connection between Vs and resistor R1. And also the connection between R1, R2, and L. And the last one, the connection between R2 and C. So let's label those nodes as this is node 1, this is node 2, 3, and node 4. And as usual, we set the bottom one as the ground node, which means the voltage at node 4 is 0. Vn4 is 0. Then we just need to find what's the voltage on Vn1 and Vn2, Vn3. To find Vn1, Vn2, Vn3, we need to apply some currents on components, right? Let's assume the current flows on R1 is flowing this way, and let's call it I1. The current flows on inductor is IL, which is flowing down. By the way, the current directions on these components are totally arbitrary. You can define I1 flows from left to right, as I shown in this diagram. You can also define I1 flows in the other direction. But since the question assume I1 flows from left to right, so I use the same flowing direction as the question gives. Alright, the current on I2 gonna be also flowing from left to right, and current on capacitor, which is named as IC, it flows from node 3 to the ground. And after you finish this step, another point you need to notice is the voltage of Vn1 is automatically given, because Vn1, this node, is connected to the positive side of Vs, and the negative side of Vs is connected to the ground. So Vn1 is Vs plus Vn4, which equals to Vs plus 0, and that is just Vs. Okay, after knowing that, we can reduce one unknown variable, and we just have two unknown variables, Vn2 and Vn3. Alright, so at node 2, we can write KCL equations. We can write the KCL equation. In case you forget what is the KCL, KCL in full name is Kirchhoff's current law, which says at a conjunction at a node, the summation of entering current equals to the summation of leaving current. For node number 2, the only entering current is I1, and that equals to the summation of leaving currents, and that is IL plus I2, right? And at node number 3, we can repeat this step. The entering current gonna be I2, and the leaving current gonna be IC. And then we just need to represent I1, I2, IC, IL by using unknown voltage variables Vn2 and Vn3. I1 is the current flowing through R1, and that is the voltage on R1, VR1 divided by R1. And VR1 can be represented by Vn1 minus Vn2 divided by R1. And Vn1 is Vs, Vn2 is unknown value divided by R1, correct? And I2, that equals to VR2 divided by R2, because I2 is the current on R2. VR2 can be represented by Vn2 minus Vn3 divided by R2, right? And Vn2, Vn3, those are unknown variables, so this expression cannot be further simplified. And the last one is IL, which can be represented by VL divided by ZL, right? And that equals to Vn2 minus 0. The other point of this inductor is connected to the ground, so the voltage is going to be 0. And divided by ZL. The last one, IC, that's going to be VC divided by ZC, which equals to Vn3 minus 0 divided by ZC. Okay. Right, so after we represent I1, I2, IL, and IC by using unknown voltage variables, we can plug these four expressions back to KCL equations, right? And we can find what's the value for Vn2 and what's the value for Vn3. So by solving KCL equations, we find Vn2 equals to, see what's the value for Vn2, that is 16.25. The phase angle is 78.43 degrees. Unit is volt. And Vn3, that equals to 7.28. The phase angle is going to be 15 degrees. Unit is volt. And after we have Vn2 and Vn3, we can find, and actually Vn2, Vn3, that is the voltage across inductor and capacitor respectively. So Vc, Vl is Vn2, Vc is Vn3, right? Alright, so the last question is, what's the value for I1 and I2? I1 equals to Vn1 minus Vn2 divided by R1, and that is Vs minus Vn2 divided by R1, and that is Vs is 2460 degrees minus Vn2 is 16.25, 78.43 degrees divided by the constant R1 is 4 ohms. And here we have the complex number subtraction. To operate that, you need to convert the polar forms into the rectangular forms, and then real part sums the other real part minus the other real part, and the imaginary part minus the other imaginary part, right? The result divided by 4, that equals to 2.5, and the phase angle is 29.06 degrees. Unit is amp. And the last one, I2, that's going to be the current flowing through R2, which is represented by Vn2 minus Vn3 divided by R2, and that is 16.25, 78.43 degrees minus, another 7.28, 15 degrees divided by R2, and R2 is 8 ohms. And here again, you need to convert the top size to complex numbers on top part in the rectangular forms. And by doing this division, the result is 2.71 minus 11.56 degrees. Unit is amp. Alright, so that's how we use nodal analysis to solve this problem. By the way, I1, I2, VL, and VC, all those are phasors, right? We just need to find the phasor representation of these parameters. If you want to find the time domain functions, you just need to you have to know the source frequency, which is not provided by this question. But if you have, let's say, if you have source frequency, then you can also represent these 4 variables in the cosine function representations. Right, so that's this question. Let's say another one. And this question can also be solved by directly solve this problem, right? Let me also show you the second method. Method number 2. Let me copy this. No, method number 2. Let me copy this diagram first. Okay. Alright, this is slide 2. Alright, so we can consider all these components R1, R2, L, and C, since they are all represented in impedance. We can just consider them as blocks, or we can simplify those components as resistors. So this is ZR1, ZR2, ZL, and ZC. And as we mentioned before, to combine impedance, the method is just like combining resistors. For series connections, we sum them together. For parallel connections, we use the formula Z1 to the power of minus 1 plus Z2 to the power of minus 1, and sum to the last one to the power of minus 1 together to the power of minus 1, right? That complex formula. Alright, so the second method we use to solve this problem is we find the total impedance first. Okay, and by observation we can find ZR2 and ZC. These two guys are connected in a series connection, right? And the combination of these two guys, ZR2 and ZC, are in parallel with ZL. And the combination of these 3 guys, right, are in series with ZR1, right? So that's how we combine these 4 components. Alright, so let's do that. ZR2 plus ZC is 8 minus 4J ohms. And this is in parallel with ZL, which is 6J ohms plus 4 ohms. And to calculate the overall impedance of 2 impedance in parallel, that is 8 minus 4J to the power of minus 1 plus 6J to the power of minus 1, and together to the power of minus 1 plus 4, right? By doing that, that equals to, so the calculation, you can do that. Let me give you the final representation. That should be 4.24 plus 4.94J plus 4, and that equals to 8.424 plus 4.94J. which can also be represented in the polar flow, which is 9.61. The phase angle is 30.94 degrees. Unit is ohms. After we find the total impedance, right, the circuit can be represented by this diagram, a voltage source and a total impedance connected in a series way, right? Two circuits connected end by end. Then we can find what's the current on this part. Let's name it as I1, and that is exactly I1, right? And I1 equals to Vs divided by Z total, which equals to 2460 degrees divided by 9.61, 13.94 degrees. And here, due to the complex number division in polar fronts, we do the ratio on magnitude parts and the subtraction on phase angle parts, and the result gonna be that's 9.61, and the result gonna be 2.5. The phase angle is 29.06 degrees. Unit is M. And after we have I1, we can find what's the voltage across this component. So let's do one step back. After we find I1, let's not combine ZR1 and this component. Let's give a name. Let's name it as Z1. Okay, that's the combination of this circle. Okay, this is Z1, and this, let's call it Z2. Okay, so the voltage on Z1, that is the same voltage on the inductor VL. So VL can be calculated by IS minus ZR1 times I1, because the current flowing through ZR1 is I1, right? And that equals to 2460 degrees minus ZR1 is 4 ohms times 2.5, 29.06 degrees, and that equals to 16.25 and 78.43 degrees point. And also to do that, you need to convert these polar fronts into rectangular fronts and some real parts together and some imaginary parts together. Right? The result is you can either represent the result in the polar front or in the rectangular front. Here I represent the result in the polar front. And after you have VL, we can find what's the current on Z1, right? Let's name the current on Z1 is IL. No. After we find V1, we can calculate what's the current on. So after we find V1, let's do one step back. This is ZL, and this is Z2, which is the combination. Z2, as we indicated here, Z2 is the combination of ZR2 and ZC. Right. the voltage on ZL is VL, and the voltage on Z2 is also VL because ZL and Z2 are connected in a parallel way. And after we find VL and Z2, we can find what's the current flowing through Z2, and that is I2. So I2 is VL divided by Z2, which is 16.25, 78.45 degrees, 0.43 degrees. That's 3. Yeah, let me make this clear. 78.43 degrees divided by Z2. Z2, as we calculated before, is the summation of ZR2 and ZC, which is 8 minus 4J ohms. And of course, you need to convert. Yes, you need to convert this 8 minus 4J ohms into the polar volt, and then do the division. The result can be 1.82, and phase angle is 105 degrees. Unit is amp. And after we have I2, VC can be easily calculated, right? And we do one step reverse. This is ZR2, this is ZC, and this is I2. The current flowing through ZR2 is the same current flowing through ZC because they are connected in a series way. So ZC, the voltage on ZC, which is VC, equals to I2 times ZC, and that can be represented by 1.8215 degrees times ZC is minus 4J ohms, right? And when you do the multiplication, you can convert this minus 4J ohms to 4 minus 90 degrees, right? And by doing multiplication, that would be 1.28 times 4, and we sum phase angles together, which equals to 7.28, and the phase angle is 15 degrees. Unit is volt. Alright, so let's compile the result as we calculated before, and you can see they are exactly the same. They have the same values, right? VC is where's the previous one? Right here. It's the same as before, as well as VN2, as well as VL, right? 16.25, 6.25. That's also the same. How about currents? I1 is 2.5, 29 degrees, which is the same as before, and 2.71 I2. Oh, that's a mistake. Here, this should be I2 here. This is a typo. I2, this one should be 1.8215 degrees. Yes, which is the same as the previous one. Right, so that's how we solve this problem by using these two examples. Right, so let's end up here. In the next class, I'm going to show you more examples and how we use other DC analysis methods like mesh analysis, Davenant's series, and other methods to solve AC circuits. But the principle is pretty much the same as I presented in this example. After we know the phasor of the source, and the impedance of all components, we can just treat this AC circuit as a normal DC circuit, and all DC analysis methods can be applied. And after this class, I'm also gonna upload a homework question set on the Canvas. The due date is 1 week from now. So today is March 18th, so the due date gonna be March 25th. March 25th. Let me know if you have any questions. You can send your questions to me by emails, or you can schedule in-person conversation with me. You can find me during my office hours in campus. Okay. All right. See you guys next time.